further applications of integration. We're going to talk about how to find arc length. So suppose we have an arc, okay? So how do you find the arc length of this? So the way that we do in calculus is we like to divide things up, okay? So in calculus, we like to divide things into small parts, and then we find the approximation for each small part, and then later on sum them up, and then take the limit as n go to infinity. Here's the idea. So for example, if I try to find the arc length of this, so what do we do? I can approximate this arc length here by this nice segment that connect straight from this point to this point, right? Now, that will be an approximation to this arc length. However, it's not a very good approximation. So I can do better. So I divide that into two arcs right here. And for this arc, I'm going to approximate this by this nice segment. And for this part, I approximate that by this nice segment over here. If I sum up these two nice segments, that will be a better approximation to this arc right here, right? And I can do it better. And I can divide this arc into even more and more small parts. And then I can approximate each part here by those nice segments right here. And if I sum them up, as you can see that as the number of parts here increase, then this is going to be a better approximation to the arc length right here, right? So that's the idea. Okay, now this is a continual function, continues on this closed interval a to b. Now what do we do over here is I'm going to divide that into n equal parts. I'm going to divide the interval a to b, this closed interval, into n subinterval, each one with equal width delta x. So now we have n arc over here, and we have n subinterval over here. Now we're going to focus, just try to find maybe on the ith interval. Okay, think about on the ith interval over here. Now notice that we start from A and end at B. When I divide this closed interval A to B into n subinterval, I'm going to label this x0, x1, x2, etc. The last one here will be xn. And the width for each subinterval here is delta x. Now I'm going to take a look at one typical interval. So let's look at the ith subinterval. So actually I'm picking one of them, say this one. And I just put it over here. Now this is the ith subinterval. So the starting x coordinate for that is x of I minus 1. And this one here will be xi. So this is the n subinterval, and this is xn. This is the I subinterval, so this n here is xi. So this is the arc over here. This is the arc correspond to this. We can approximate this arc over here by this nice segment that are joining the two ends, this point pi minus 1 and pi over here. So this arc over here is approximately equal to the length for this nice segment over here. So this length for nice segment and this length for the arc right here. Now let's try to express this, okay? Express this in terms of delta x. Now this is a y triangle, and this is delta x. This is the change in y, but it is a change in y on the I subinterval, right? So I call this delta yi. By the Pythagorean theorem, what is an expression for this nice segment? What's the length for this nice segment over here? Anyone?
Square root of x squared plus y squared.
You got it. So that's the square root of delta x squared plus delta yi squared, okay, by the Pythagorean theorem. Okay, later on, we want to turn that into an integral to find the arc length. So how about we express this delta yi in terms of delta x? Because later on that will become a dx. So let's try to express this in terms of delta x. So we want to turn that into an integral with respect to x later. Express that in terms of delta x, okay? Now how can we do that? Well, remember the mean value theorem that we talked about. The mean value theorem, it says that if a function is continuous on this closed interval a to b, and is differentiable on this open interval a to b, and then there is at least one point on the curve, that the tangent line is going to parallel to the secant line over here. Remember you saw that equation on the bridge in Beijing, right? which is the same equation you see here on this bridge. This photo was taken in Beijing, the capital of China. In 2008, the government of Beijing celebrated the mean value theme and put it on the bridge. Now imagine that the mean value theme is celebrated here and it is put on the Bay Bridge. So when you walk along the bridge, somewhere on the bridge, then the tangent line is going to parallel to the base of the bridge. This function over here, the function f over here is continuous. Okay, it's continuous. There's no break, and we assume that it's differentiable. The duality exists. So think about this like the bridge. Okay, and this is the base of the bridge right here. So when you walk along over here, somewhere on this bridge, then the tangent line is going to parallel to the base of the bridge. You got an idea, right? Okay, so I'm going to highlight that one. So somewhere between the two ends, somewhere between xi minus 1 xi, there is a number. Let's call this, well, because this is the I subinterval, so let's call that xi star. Okay, don't be intimidated by those symbols. This is on the I subinterval, and xi is this right endpoint here. So this point over here, I put xi star. The star here indicates this point here is on this I subinterval and distinguish between this xi. So the mean value theme says that the slope for this tangent line is going to equal to the slope for this secant line here. So let's write it down. So slope. Then this slope here will be equal to the slope for the secant line over here. Okay. Now the slope for this tangent line over here, remember slope corresponds to the first derivative, and this is the function f, right? So I have this f and the first derivative, and it is at this point, so xi star. So the slope of the tangent line at this point is f prime of xi star. Now what about the slope for the secant line pi minus 1 pi? What's the slope for the secant line here? Looking at this diagram, what's the slope for this, the orange secant line over here? There's rise over run, right? What's the rise and what's the run? Anyone?
Delta y I over delta x.
You got it. So delta yi over delta x. Okay, so now remember, we are trying to express this delta yi in terms of delta x. So over here, let's express this delta yi in terms of delta x by multiplying delta x on both sides. So now we got delta yi is equal to, now let's substitute this back. Let's substitute this back into this. So P of, so I have this P of I minus 1 pi, this nice segment over here is equal to the square root of delta x squared plus the square of this delta yi, which we already found out it is this f prime minus star delta x.
That's the length, right? The pi.
Yes, that's the length. Yeah.
The
remember,
pi, whatever that symbol is.
yeah.
Pi.
This is the length, okay? So that's the length for this nice segment over here.
Okay.
That's the length for this. So that's pi minus 1 pi, and this stands for the length of this. Okay, and I'm just substituting this back into this delta yi. So that's what I have done. Okay, now I get this expression right now. Now remember, we're trying to take the delta x out. So what do I do over here? We will take out this common factor delta x square, right? And then over here in front, we'll have, over here, we will have 1 plus f prime xi star. But don't forget, there's a square there, okay? So there is a square over here. Let's use a different color. So there's a square over here, remember? Okay. So this one here will be a square. I want to use a parenthesis. Okay, square. And then for this one, let's use the bracket over here. So I'm taking out this delta x squared as a common factor. Take it out like this. Now, after that, when you take the square root of this product, so you take the square root of each factor. So this will be the square root of 1 plus f prime xi star square. And then outside we'll have this delta x, right? All right. Okay, so this is an expression for that, the length of this line segment. This corresponding to the length of the line segment on the I subinterval. Now we're going to sum up all those line segment for n subinterval. So we have this, the sum of n those small line segment. So we're going to sum them up. So then we're going to get, remember, so this pi minus 1 pi. This is one line segment on the I subinterval. And now we have n of them. So I will go from 1 to n. So try to imagine this. Remember, you can try to imagine this. So each one of them, you use a line segment to approximate the arc length. Now you're going to sum them up. So this is the sum right here. Now this is equal to, I go from 1 to n. Now we have an expression for this, right? Okay, so now we're going to put this in here. And then outside here it is delta x. You got with me? So I'm just replacing this by this, okay? Because this is an expression for this line segment, the length of the line segment. Now this is the sum for those n small line segment. Now we're going to let n go to infinity, okay? Just like before. So we're going to let n go to infinity. When you let n go to infinity, and when you sum up those n line segments, they will getting closer and closer to the arc length, okay, right there. So, and this is going to become an integral, right? The summation sign here become integral sign, okay? And square root. The delta x over here, we're going to replace by dx, become dx, okay? And what should I put inside this square root right here? 1 plus what? F prime of, now instead of xi, we're going to replace this xi over here by x, and then you square this. X over here, remember this is continuous function. Remember that this one over here, okay, just say this is a function f, okay. It is a continuous function. It's also a smooth function, okay. It is continuous on this interval a to b. A start from A and then B, where this x over here is greater than or equal to A, less than or equal to B. X is somewhere between A and B. So when you have this function that's continuous on this quotient of A to B, then this arc length over here, let's call that L. Okay. So what color should I choose? Let's choose. Let's choose. Let's choose this. So the arc length over here, let's call that L. L is equal to this integral. And x over here will start from A and end at B. So A here and B over here. So this is the arc length formula. So arc length formula. So after all this work, you guys discover this arc length formula. So it is going to be, if you want to find the arc length, it will be this integral, the integral of 1 plus the square of the first derivative, okay, where, yeah, and you take square root of the 1 plus the square of the first derivative, and then x here go from A to B, okay, so that's the arc length formula. Now, we call that, another way to write f prime of x is dy dx. So if y is equal to f of x, then dy dx is the same as f prime of x, right? Okay, so that's the same as f prime of x. So another way to write this formula here is to replace this f prime of x by dy dx. So we can have this arc length formula. So the arc length, now that's equal to this integral, the square root of 1 plus dy dx square, okay, and integrate with respect to x goes from a to b. So this is another way to write the formula. Notice that over here, what we have done, it is we have this closed interval AB, and the function and the graph is continuous from A to B. Okay, and what we have done over here when we try to divide the formula, okay, so we divide that into subinterval, right? Each with equal width. Okay, the equal width here will be delta x. Okay, so then you have this dx over here. Okay, and we got this formula. So let me. Okay, so that's the arc length formula. You guys have question about this? Now pay attention the square over here. Don't forget the square on the derivative over here because we actually use the Pythagorean theorem, okay, when we divide this formula. So that's the square over here. Okay, so when the r is oriented this way, okay, we divide it this way, slice it up this way, okay, and we got this formula. What about if I have, so suppose this is the y-axis, and the arc that we have is going to be like this, like that. Now, for this one, I cannot use this formula. I cannot use this formula because this, you see, this is, the y here is not a function of x, right? It doesn't pass the vertical line test, right? So that is not a function of x. Now, but it's a similar idea. We can find this arc length over here by dividing this. Okay, suppose this one start from C here and end at D over here. I can find this arc length over here by dividing this. From C to D, we divide into n subinterval. And then we can approximate each arc over here by those 9 segments, like that. And then we sum up those n 9 segments and let n go to infinity, and we should get this arc right here, right? So it's a similar idea. So the arc length for this is equal to the integral. Now this time, because we divided this way, then each subinterval here, it is delta y. So this should be a dy outside. This should be a dy there, okay? And similarly, we will have this square root. And y over here go from C to D. So C here to D over here. Now, what do you think? Okay, let's compare this. Compare this one and this one. Let's compare this one with this one. This one over here, you got this expression for the arc length. This one over here, what do you think? What should I put in this square root? Instead,
1 plus dx over dy squared?
yes, you got it. Okay. So instead of dy dx over here, now we have a dx dy. Okay. So we'll have 1 plus the square of, this time we'll have dx dy right there. The idea is similar. Okay. So this will be the arc length formula if the arc is like this. Okay. Then you can slice it this way and you find this arc length. Okay. So I'm going to circle this also. Okay. Okay. Now you might have so now let me ask you this. So suppose you have this, suppose this is x-axis and y-axis, and the arc that you have is like this. Okay. So which one you use? Do you use this one or this one? This one or this one? Or you can use both. What do you think?
I think you can use either.
you can use both, either one's okay, okay? Because you can slice it this way, right? So you can slice it this way. Then you have this delta x, right? Okay. And then you can also slice it the other way. So if you can slice it this way. Okay, you slice it this way. And then there will be delta y. So you can do it either way. Okay. So if the r is like this, okay, then you either use this formula or this formula to find the arc length. Depends on which one is easier to find. Is dy dx easy to find or dx dy easy to find? And then you will choose the easy one, okay? So in this situation over here, so you can, this one here, you can use either, let me label this. Let's call this A and this B. So you can use either A or B. Okay, either one's okay. Question? Okay. Okay, now let's do one example. Okay. So we have this equation, y squared equal to x squared. Okay. And this is called a semi-cubical parabola. Oh, wait, it's not, no, sorry. It's a y squared equal to x cubed. Okay. So this is called a semi-cubical parabola. Okay. Now, let me graph this for you. Okay. So x-axis and the y-axis. At the first quadrant, the graph is going to be like this. Okay, like that. And passing this point, let's say 1, 1, 1, okay? And also passing this point, when x equal to 4, y over here will be equal to 8, okay? So passing this 2 points, 1, 1, and 4, 8. So the question over here is, we're trying to find the arc length over here. Let's say the arc length over here, which is this one over here, this arc length from here to here. So we're trying to find this arc length. Okay, let's call it L. Okay. Okay, so you get the idea. Okay. Now this one over here, as we mentioned before, it looks like it is like this, right? We can either slice it this way or slice it this way. You can actually either use either A or B to do it for this one. Okay. So the arc length over here, let's call that L. Okay. That's equal to, which one you think is better? Which one you want to use, A or B?
A, please.
A first. Okay. All right. So let's use A first. Okay. So if I use A, so the formula says that this is dx, right? X go from where? From 1 to 4, right? And then inside here we'll have 1 plus, this will be dy dx, and then square. Okay, like that. That's I'm using A. Okay. So using A over here, So to find this, we need to find dy dx, right? So let's find dy dx on the side. So we have y squared is equal to, we have y squared is equal to, different color. Y squared is equal to x cubed, okay? To find dy dx, let's solve for y, okay? Solve for y. To solve for y, remember we are at the first quadrant, right? The graph over here is at the first quadrant. So at the first quadrant, the y here, it is positive, right? Y is positive. So I only take positive root of this, okay? So the y over here will be equal to positive square root of x cubed, which is x to the 3 over 2 exponent, okay? Okay, so now we solve for y. Now we can find dy dx. So dy dx is equal to what?
3/2 square root 3.
3/2 x to the what power?
I mean square root x, sorry.
Yeah. Yes, you got it. Okay. X 3/2 times x to the 1/2 power, right? And now we're going to square this, right? So let's square this. Dy dx squared. So that's equal to what? 9 over 4 times what? Times just x, right? Square x to 1/2 power, it is just x, okay? X is positive, okay? Okay, now we can put this back into this, okay? Let's put it back, okay? So that's equal to this integral 1 plus, we just got this 9 over 4 times x, dx, x go from 1 to 4. Okay, how do you evaluate this integral? By hand, okay, not using the device. So what kind of integration technique would you like to use?
Would you use like I'm just looking at the integration strategy notes that you gave, and maybe wait.
Could just be a U sub.
Yeah, U sub.
Yeah, just use.
Okay, so we want this whole thing inside to be a single variable. So let's use U sub. Okay, so U sub. Okay, so we're gonna let U to be. Okay, so U over here. Okay, so U is equal to 1 plus 9 over 4x. So du will be equal to 9 over 4 dx. Okay. Now this is going to change. Remember, you need to change the upper and lower limit once you do the U sub. Okay. So over here, let's write down for this U. Okay. When x equal to this lower limit 1, what does U equal to? U is equal to we'll do the calculation. Okay, so that is going to be 13 over 4. So the lower limit for the u here is 13 over 4. Don't forget to change y here. And when x equal to the upper limit 4 over here, do the calculation, u is going to be equal to 10, right? Okay, 10. So 10 is upper limit over here. Okay, so you need to change upper lower limit after you sum. Okay, now this one over here is going to be square root of u, which is u to the 1/2 power. Okay, and then the dx over here is going to be 4 over 9 du. So this will be 4 over 9 du. Okay, so from this you will have dx equal to 4 over 9 du. So that's why you have this. Okay. Okay, and then u over here, this is an integration with respect to u. So u over here change from this to this. Okay. Now after that, we will take out this 4 over 9. Okay. And what's untitled to u to the 1/2 power with respect to u? So that will be u to the 3/2 power, right? And then multiply with 2 over 3, the reciprocal of that. Okay. And then remember, the u here changed from 13 over 4 to 10. And then you just do the calculation. Okay. So this is going to become 8 over 27 times, over here will be 10 to the 3/2 power, subtracting 13 over 4 to the 3/2 power. Okay, now this will be correct. Okay, so this will be correct. Okay, so this is right. Okay, now sometimes the book write it the other way. Another way to write this is 8 over 27. This is 10 square root of 10 minus 13 over 4 times square root of 13 over 4. And then you can further simplify this. This part over here, it is square root of 13 over 2. So you write this as 8 over 27. Okay. Now because this 8 over here, okay, and this, and then the book actually multiply this 8 inside. So the book write it this way. So 1 over 27, and then this will be 80 square root of 10 minus 13 square root of 13. So I think they should accept all this answer here. So all of them are okay. So all of them. Those are called exact answer. So if they ask you for exact answer, don't use approximation. So keep those roots and those power like this. Okay. Okay. So now someone say, well, you use A. How about you use B? Okay. Now another way to do this is to use B. Okay. Because we have so when you use B, you slice this, right? So you slice it this way. Okay. And each one will be delta Y, right? So delta Y. Okay. And over here, Start from 1 here and end it at 8. Okay, so we can actually find this arc length using B. Okay, so we have this y squared equal to x cubed. So this arc length over here, this L, when I use B. So what integral this correspond to? So this time instead of dx, so we're going to have dy outside. Okay, and y here go from 1 to 8. What should I put into this square root? 1 plus what? Dx dy square, right? Okay. So how do you find, and then now you try to find dx dy, okay? So how do you find dx dy? So you have y squared equal to x cubed, okay? You can solve for x over here. Solve for x. So you take cube root on both sides. So x is equal to y to the 2 over third power. Okay, so over here you take cube root on both sides. Okay, and now dx dy will be equal to what? 2 over 3. Okay, and then y to the what power? Are you guys there? So y to the
You have 5 over 3?
negative 1 third power.
My bad.
Okay, and then after that, you will just substitute, right? So you substitute this back. So, and then you just substitute back right here. And then you can use calculator to find that. So the answer should be the same, okay? You should get the same answer. Okay. Now it's 12 o'clock. The next one here is going to take about 10 minutes to 10 or 15 minutes. Do you guys want to go over one more example, or you want to call this a day? Another 15 minutes.
We can do one more.
We can do one more? Okay. Right. Be prepared. It's really long. Okay. Okay, so let's do this. Okay. So this example over here, we have y squared over here is equal to x, which is the same as x equals y squared, right? We know how to graph this. This is a parabola open to the right. So this is a parabola open to the right. Oh, wow, perfect. Okay. So over here, say this is going to be, so it's 1, it's also 1. Okay. Now over here, we only focus on finding the arc length from here to here. Okay. Find this arc length over here. Let's call it L. Okay. So you want to use formula one, A or B? Which one for the arc length? Which one is easy to find? You want B? Yeah, good choice. Good choice. Okay. So y squared equal to x. Okay. Let's see over here. So dx dy is actually easier to find, right? Because x is expressed as a function of y. So dx dy is easier to find. Okay. So because of this, is easier to find. So we want to use dx dy. Dx dy over here, it is equal to what? It's equal to 2y, right? Okay, so that's equal to 2y. It's just easy to find. So we're going to use b. Okay, so I'm going to use b because of that. Okay. It's easy to find. So therefore we use this. Okay. So this is the integral. Now outside here we'll have dx. Okay. And then square root. So 1 plus, this time we'll have dx dy. Hold on. Hold on. Did I make a mistake? Is this not dx? What is it? What's this one? Dy. Okay. So notice that, see the dx dy. See the dy here, match with this dy right here. Okay. So the square of this. Okay. So that's the dy here. Okay. Y here go from 0 to 1. So 0 to 1. Okay, so we use this. Okay. So that's equal to square root. Okay, now we have dy outside. Okay. This is going to be 1 plus dx dy, it is 2y, so 2y squared. Y go from 0 to 1. Okay. So it looks like a very simple integral. Okay. However, if you do it by hand, how would you like to, what kind of integration technique that you use to find this integral?
Is it trig sub?
Yeah, good job. Okay, you guys are doing great. Give you a thumbs up. Okay, so trig sub. Okay, so we use trig sub. Okay. So what made you think about trig sub? Because
Sorry.
yeah, I know you know that. Okay, so because this square root of, remember, a squared plus x squared, right? And because this is the square root of a number plus a square over here, so it's involved this form. So that will make you think about trig sub. Okay, so okay, so we think about trig sub. Okay, so think about this 2y over here. It's like this x over here. Okay, so when you use trig sub, now remember this corresponds to this identity. The a squared corresponds to the 1. Think about correspond to 1 plus what square over here equal to what square. Because you want to have a perfect square inside, so then we take square root, then we can get rid of the square root, right? So we want to have a perfect square like this. So think about 1 plus what square equal what square. What should I put here?
Tangent?
Tangent, yes, tangent. So this is going to be tangent, right? Tangent of theta. Tangent of theta, and then that will be equal to the square of secant, right? 1 plus tangent square equals secant square. So over here, then this is equal to, so the trig sub over here, we're going to have this x over here. So trig sub, we will have this x equal to what? Well, over here, if you have this, x will be equal to a tangent theta. So you will have a tangent theta. Where theta over here is going to be between negative power 2 to power 2. So when you do this trig sub, then this square root over here become a what? A secant theta, right? A secant theta over here. A secant theta over here. Match with this, okay? Okay, now go back to this one over here. So we're going to let this, we're going to do trig sub. So I'm going to let this 2y, okay, equal to a tangent theta. A here it is 1, okay? A is 1. So that will be tangent theta. So that's equal to tangent theta. Then y over here will be equal to 1/2 tangent theta. So then what about the dy? So what does dy equal to? Dy will be equal to 1/2. The derivative of tangent is what? Secant square, right? Secant square theta and then d theta. So you're going to replace this dy by this, okay? Now, once you use trig sub, then this part over here become this integral. This square root over here, it becomes secant theta. Okay, so we have secant theta. And the dy over here is replaced by this. So 1/2 secant square theta d theta. Now don't forget to change the upper and lower limit here. Okay, those are for y, and let's find out what happened to theta. Okay, that's really long. Okay, so tangent theta is equal to 2y. So we have this. So when y over here is equal to this lower limit 0, tangent theta will be equal to 0. So remember theta is between negative power 2 to power 2. So what does theta equal to? Theta will be equal to 0, right? Theta will equal to 0. I'll try to choose a different color. Okay, theta equal to 0. So
Yeah,
the lower limit.
I have a question.
Yeah?
How did you get from tangent theta equals 2y to y equals?
Okay, this is when y equal to 0. When y equal to 0. When y equal to this
Oh, okay.
limit of the integral.
Okay.
Yeah. So when y equal to this lower limit of the integral over here,
Okay.
which is 0, the tangent theta will be equal 2 times 0, which is 0. Then theta will be equal to 0 because theta is in here. Okay. Now, when y equal to the upper limit, which is this 1 over here, this upper limit 1 over here, so this is the upper limit, then tangent theta will be equal to 2. And this is, then theta here is not a special angle. So theta will be equal to, let's express it as the inverse tangent. So that will be the inverse tangent of 2. So inverse tangent 2. Now, because if I put inverse tangent 2 over here, it looks very too much. So let's just write this as alpha. Okay. So let's call this alpha. Let's call this alpha. Okay. Now remember alpha here is inverse tangent of 2. Now let's take out this 1/2 over here, this constant multiple. So you have 1/2. And then the integral here go from 0 to alpha. And this is secant q theta d theta. It looks kind of simple. However, I wonder if you can remember the formula. Because antiderivative is secant q. I give you $1 if you remember. Anyone?
So like negative cotangent theta minus theta? No.
No. Let me try it again. Okay, so this is 1/2. Okay, now let me tell you that. I don't remember that either, okay? Look it up. So it is going to be 1/2 secant theta tangent theta plus 1/2 ln of the absolute value of secant theta plus tangent theta over here. Yeah, I don't remember the either, to be honest. Okay. And then over here, theta go from 0 to alpha. Okay. All right. So that is the antiderivative of that. Okay.
So,
now,
wait,
yeah.
So we don't have to use like some.
Yeah, we actually got this before. I think we did this before, long ago.
Okay.
So all you have to do over here, now 1/2 times 1/2 is 1/4. Okay. Now this is going to become secant alpha, right? Substitute alpha in it. Okay. And then tangent alpha. And then plus, remember the 1/2, we take out the common factor 1/2. Okay, so 1/2 is out. Plus ln of this absolute value of secant alpha plus tangent alpha. Okay, so you substitute the upper limit alpha in it. You got this part right here, right? And now you subtract, right? So you subtract this whole thing. Subtract Now you substitute 0. You're going to substitute this lower limit 0 into this and this. Okay. When you substitute 0, so let's just write it down first. I know some of you already see tangent of 0 is 0, right? Okay. So tangent of 0, and then plus ln of this secant of 0 plus tangent of 0, right? Okay, right? I'm just substituting, okay? I'm just substituting alpha in it and substitute 0 in it, and then over here subtract, right? Okay, let's take care of the easy part first, okay? Tangent of 0 is what? Tangent of 0, it is 0. So 0 times anything is 0. So this term here becomes 0. Okay, and tangent of 0, it is 0. Secant of 0, it is 1. Now, ln the 1, what's ln the 1? Ln the 1 is what?
0.
0.
It's 0. Okay, so it is 0. So this part here becomes 0. Okay, let's focus on this part. Okay, so what do we have over here? Okay, remember, okay, we call that alpha. What's alpha? Alpha is inward tangent of 2, right? So what does it mean? That means tangent of 2 is equal to sorry. That means tangent of alpha is equal to 2. Okay, that means this. Okay, which is the same as 2 over 1. Now we're going to use our trick. Okay, the trick over here it is to use the y triangle. Okay, so we have this triangle here, and you label this angle here alpha. Okay, tangent alpha is 2 over 1. So let's label the opposite side here 2, adjacent side here 1. By the Pythagorean theorem, what will be this hypotenuse? Square root of 5, right? Square root of 5 by Pythagorean theorem. Okay. So now by using this y triangle, you can find out secant of alpha, right? So we try to find the secant alpha right here. Okay, let's figure out what the secant alpha here equal to. So secant of alpha is equal to what? Secant is a reciprocal of cosine. So that will be hypotenuse over adjacent. So that will be square root of 5 over 1. Remember, this is hypotenuse. This is adjacent. So that's equal to square root of 5. So now we can substitute this back. Okay. So this part over here will be just square root of 5. Tangent alpha, it is 2. Secant alpha is square root of 5. Tangent alpha is 2. So finally, we can write this. So that is equal to 1/4. And this will be 2 square root of 2 plus ln of. Now the absolute value is not necessary here because we're taking ln of a positive, so I can just use parentheses instead of the absolute value. So that's the final answer over here. Okay, you guys got it?